So before we go ahead, let me just make a few small corrections. Since we're talking about the frame S prime, we should rather use X prime, T prime over here, and similarly X prime and T prime over here, since we're describing the position and times at which we're observing this wavefronts as X prime and T prime in the frame S prime. And this is X hat prime, Y hat prime. Which of course we'll assume that if we take a second observer, their axes are aligned. Okay. And more precisely, let's also put down nu as nu prime. That is, this is the frequency of the wave as seen in the frame S prime, and lambda prime is the frequency of the wave as seen in the frame S prime. So let's put primes on everything. Okay, we don't know for sure if these directions or the wavelengths or the time periods would be the same as seen by a second moving observer. So we're going to work out what a second observer moving relative to the frame S prime would see. So now if we consider a frame S, we'll assume that again the axes are oriented in the same way as observer S prime's axes. And we want to ask, what would observer S see for this plane wave? Okay, what is the equation that would describe, let's say, the phase of this plane wave for them? So the question is, what would observer S see as the phase of this plane wave? Now, both observers, if they're looking at a particular location, so they're looking at a particular space-time point, so if both observers are looking at a particular space-time point, we of course know that they will have different descriptions of the coordinates of that space-time point. But they must agree on the phase of the wave at that particular space-time point. Now, why should that be true? Well, the phase of the wave is related to a physical property of the wave. It tells you whether there's an amplitude maximum or a minimum. And that amplitude maximum could, let's say, trigger some other reaction. So therefore, whether you have a maximum or a minimum or some intermediate phase, both observers should agree on the value of that phase. Okay, so the phase is not relative. The phase is something that both observers will agree on. They will just disagree on the description of the location of that space-time point. And so if they disagree on the location of that space-time point, they might also disagree on the frequency of the wave and the wavelength of the wave. In fact, we would expect them to disagree, since we know that time is measured differently in frame S as compared to frame S prime. And lengths are measured differently, so the wavelength should also change in frame S relative to the frame S prime. However, the thing that should still be the same is the speed of light as measured in the frame S. Okay, so let's now work out what would, let's answer this question. What would observer S see as the phase of this plane wave? So observer S would measure exactly the same phase as observer S prime at the same space-time point. However, observer S would measure a different wavelength and or wave vector k bar, and they would measure a different frequency omega. They would, however, or they should, however, measure the same speed c for a light wave. Okay, this is not true for other waves, but for light waves, they should measure the same speed c. Now, in the frame S, we will assume that the vector k bar has a magnitude 2 pi by lambda, where lambda is the wavelength measured in frame S, and the vector k hat, or the direction of propagation, makes an angle theta with the x-axis. Okay, so this angle theta need not be the same as theta prime. Okay, so which is the angle made by the wave with the x-axis in the S prime frame. So to be more general, we'll assume that k hat makes an angle theta, and therefore the phase of the wave measured in frame S can be written in the form 2 pi times nu, where nu is the frequency measured in frame S, t is the time description of a particular location in the frame S, minus k vector dot x vector. Okay, where nu is the frequency measured in the frame S, t is the location of the space-time point at which you're trying to find the phase, as described again in frame S. K vector is the wave number vector, or the wave vector, again described in frame S, which has a magnitude which is related to the wavelength in frame S, and it makes an angle theta with respect to the x-axis, again as measured in the frame S. And x vector describes the position at which you're trying to describe the phase of this wave. And this again, we should be able to write it as, oops, sorry, I made a mistake. Here we should actually write angular frequency. And when we write it in terms of frequency, we can write it in this way: nu times t minus x cosine theta plus y sine theta divided by lambda. Now, if the speed of the wave as seen in frame S is also c, then we should have that lambda over the time period as measured in frame S should be c, or equivalently lambda times the frequency as measured in frame S should be c. Okay, so over here in frame S prime, lambda prime times nu prime should be the speed c. Okay, so now this phase should be exactly the same as the phase measured by S prime at the same space-time location. So what that means is, if tx and t prime x prime describe the same space-time point as measured or as described by S and S prime respectively, then it should be true that the phases then nu times t minus x cosine theta plus y sine theta over lambda should be equal to nu prime t prime minus x prime cosine theta prime plus y prime sine theta prime over lambda prime. Okay, this is the statement that the phases agree at the same space-time point. Now we can use our dictionary and write x prime, y prime, and t prime, okay, in terms of x, y, and t. So now we can use our dictionary to write x prime, y prime, and t prime in terms of x, y, and t. So if the frame S prime is moving with respect to S at a speed v, what we then have is the dictionary tells us that x prime is equal to 1 over the square root of 1 minus v squared by c squared into x minus vt. Y prime is y, and t prime is 1 over the square root of 1 minus v squared by c squared t minus vx over c squared.